My dear students, I welcome you all to another lecture on SSSC. This is lecture number 2 on SSSC. We have already discussed the basic structure of SSSC, that is static synchronous series compensator, and its operating principle. And today's lecture is continuation of our discussions on SSSC. Now, first of all, I will try to show you how power flow reversal takes place in an SSSC. Okay, so let us try to understand how power flow reversal occurs. So it is something like this. For example, this is omega t axis. So let us suppose this is the phase, since our SSSC and our transmission system is a three-phase system. Sorry, I may have to draw a slightly compressed waveform. So let us suppose this is phase voltage VA. Okay. Now, I have drawn 3 cycles of phase voltage, and I am drawing the current, line current IA or phase current IA. This is the line current or phase current IA. I am showing it in phase with the voltage, assuming unity power factor, but it is not necessary. It could be out of phase with voltage. This is IA. So here I am showing no compensation. I am not doing any series compensation by SSSC. I am writing here no compensation. Right? Let us assume current is lagging behind voltage by a small phase angle. Okay? You can see a small phase difference is there. So this is phase A voltage. Okay? Transmission bus voltage, and it is transmission line current pertaining to phase A, line current IA. So it's no compensation. Now in next 3 cycles I will draw, and I will assume that we are using SSSC for compensation for positive power flow. Okay, compensation for positive power flow. So let me first of all draw 3 cycles of voltage waveform again. So this is 1, 2, and this is 3. In fact, I can increase 1 half cycle. So now I am showing this is compensation for positive power flow. Positive power flow. Positive power flow, we mean that the power is flowing from sending end to receiving end. For example, if you draw the diagram again, this is the voltage injected by SSSC, injected voltage, and this is transmission line reactance XL, and voltage across it is VL, and this is 2 machine model of our transmission system. This is sending end voltage, this is receiving end voltage. Current is flowing in this direction, and positive power flow means that power is flowing from sending end to receiving end. How is that made possible? That's made possible if SSSC injects a voltage VQ, okay, which is in phase with this transmission line voltage, so that the total voltage across the transmission line is VQ plus VL. So VL dash is equal to VQ plus VL. We have already studied it with the help of phasor diagram in the last lecture. So overall voltage across the transmission line increases, which increases the current. And when current increases, the power flow also increases, and power flows from sending end to receiving end. So we are doing compensation for positive power flow. That means we are compensating this transmission line in order to increase. Here also it is without compensation also, this transmission line is transmitting certain amount of power. But with series compensation by SSSC, the power flow over the line increases. We are increasing the power transfer capability of the line. The power transmitted over the line increases. How is that done? That is done by using SSSC, which injects a voltage VQ, and this voltage increases the overall voltage across the line, which is VL plus VQ plus VL, and hence it increases the current I, and hence it increases the power flow over the line. So the current, this is again VA voltage. Now current previously was smaller in amplitude. Now current will increase. It will increase because we have done the series compensation. So because of this series compensation, you can see the current magnitude or current amplitude is increasing. And since current IA has increased, what will happen to power? Power flow will increase, and power will flow from sending end to receiving end. We know that power flow PQ or P is equal to V square by XL minus VQ by I sine delta. Okay, so without series compensation, that means in this case, power for uncompensated line, P is equal to V square by X sine delta. Okay, so this much of power is there. Current is there, voltage is there, certain amount of power is flowing over the transmission line. After doing series compensation by SSSC, by injecting a voltage VQ, so in terms of reactance, the reactance of the total reactance of the line decreases. It's not XL now. Previously it was XL. It's now XL minus VQ by I. So it decreases, so power flow over the line increases. And in terms of voltage, we can say that the total voltage or effective voltage across the line increases, which is, it is VQ plus VL. That increases the current. You can see current previously was smaller in amplitude. Now it is increasing, and therefore power flow over the line increases. And this is the positive power flow. Positive power flow means power is flowing from sending end to receiving end. Now, next few cycles I will show using the compensation for negative power flow. Okay. Let me first of all draw, now this is my voltage. Let me add one more half cycle here for better clarity. Now next few cycles I will show. This is again voltage, 1, 2, 3, say 4 cycles. This is again phase voltage VA. Now, what will I do? I am now doing the compensation for negative power flow. I am using the same compensator, SSSE, but now negative power flow. Negative power flow means the power will flow from receiving end to sending end. That is possible only if direction of current reverses, instantaneous direction of current reverses. For positive flow, the direction of current was here, like this, and for negative power flow it has to reverse, and therefore power flow also has to reverse. And I have already told you condition. What is the condition? And you have seen from the P delta power angle characteristics also in the previous class that one of the peculiarity or one of the uniqueness of SSSC series compensator is that if the injected voltage VQ is made greater than the difference of sending end and receiving end voltages. If VQ is greater than Vs minus Vr, then the direction of power flow reverses. Power, instead of flowing from sending end to receiving end, will flow from receiving end to sending end. So therefore, I am still injecting voltage VQ, but I am now increasing its magnitude. Injected voltage I am increasing such that it is greater than the difference between sending end and receiving end voltages, and direction of power flow reverses. So when direction of power flow reverses, it is something like this. See, current reverses its direction, so that reverses the direction of power flow. So this is the current. So this is the current I. Now you can very clearly see IA. Voltage is negative, current is positive. Voltage has positive half cycle, current has negative half cycle. And what is power? Power is the product of voltage and current. And since current is in phase opposition to voltage, it is minus IA. So therefore power and some cosine of phi, so it is minus, it is negative, because one of the quantities is negative. Positive VA multiplied by negative IA becomes negative, and negative power means that power is not flowing from sending end to receiving end. it is flowing in the opposite direction. It is flowing from receiving end to sending end. And I have already told you the condition for that is that the injected voltage VQ should be greater than Vs minus Vr difference, right? So I hope this is clear. Now, so here I will write compensation for negative power flow. Negative power flow. So I am adjusting the injected voltage of the compensator in such a way that instead of positive power flow, the power flow is now negative. It is not flowing from sending end to receiving end. It is now flowing from receiving end to sending end. Now regarding active power and reactive power. So let me show you active power and reactive power. So for example, active power here, without compensation, certain amount of active power P is flowing over the line. And then when I am doing the compensation using SSSC for positive power flow, current increases, the power also increases. So more power is now flowing over the line, but positive power. And then here, what we are doing, we are using compensator for negative power flow. So direction of power flow is now reversed. You can see it's negative power flow. Okay, so this is P. This shows P. What about Q? So since here current lags behind voltage by certain amount, so some reactive power is required by the load, some reactive power flows, and that reactive power is supplied by your compensator. So a small amount of reactive power because of this phase angle difference. And then when we are doing positive power flow compensation, I already told you just few moments back, this compensation for positive power flow is possible only when injected voltage VQ, here VQ is 0, no voltage is injected. Now some voltage VQ is injected with the help of this injection transformer by SSSQ plus minus, and this we know that this voltage VQ, for example, if this is current I, the voltage VQ lags behind the current by 90 degrees. In other words, if you multiply this injected voltage by transmission line current, they are in quadrature, so it represents the reactive power. So that means the reactive power increases. Now certain amount of reactive power which is injected by, which was very small for no compensation, it will now increase because now compensator is injecting a voltage VQ which is in quadrature with the current, and hence the reactive power increases. And it is because of this reactive power, we are doing a sort of reactive power compensation that increases the power transfer capability of the line. You can see active power increases. So it is because the reactive power we are increasing slightly. So this is the increase in reactive power. And then for negative power flow, again, injected voltage is there, current is there. So, but you can see if this is injected voltage, so now what happens is that the direction of current has reversed, and this is your injected voltage. This is your injected voltage VQ. They are still in quadrature, but now current is again leading the voltage, but you can see direction of current has reversed, so the reactive power has also reversed. So reactive power reverses. You can see it reverses, and this becomes the reactive power Q. So for no compensation, small reactive power is injected by your compensator SSSC to take care of the reactive power which is flowing on the transmission line. For positive power flow compensation, reactive power injected increases, and for negative power flow compensation, the reactive power is then negative. So this is active power, this is reactive power. Okay, in the next graph, I will show you the current and the injected voltage, the relationship between current and injected voltage. Now, so for example, this is current, 1, 2, 3 cycles of current. This is current, and what is injected voltage? VQ is equal to 0, because during these 3 cycles, we are not doing any compensation, no compensation. So although SSSC is connected there, but it is not injecting any voltage. So VQ is equal to 0. And then here we are doing this what we call as injection is done. This power flow over the line increases, because of the SSSC injection. Now SSSC is injecting a voltage VQ which is in quadrature with current, and since the reactive power is injected, so therefore current should lead the voltage. That means reactive power is injected, that increases the power flow capability of the line, positive power flow capability of the transmission line. And earlier active power flow was less, now it is more. Okay, it is because of compensation by SSSC. What SSSC does, it injects a voltage VQ which is in quadrature with the current. Now what will happen to the current? Current will increase. As you can see here, current, for no compensation, magnitude or amplitude of current was less. Now when compensation is done, amplitude of current increases. Let me show you 1, 2, 3, 4 cycles. I have shown 3 and 4 cycles. 4 cycles. So this is now current. And there will be injected voltage, injection of voltage. And this is the injected voltage, VQ. Let me first of all draw it, something like this. This is injected voltage VQ. You can very clearly see when current is at its peak, injected voltage is 0. When current is 0, injected voltage reaches its peak. That means injected voltage is lagging behind the current by 90 degrees, or in other words, current is leading the injected voltage by 90 degrees. That means if this is the current, this is injected voltage VQ. VQ lags behind I by 90 degrees, or I leads VQ by 90 degrees. That means reactive power is being injected into the system. That's why you can see reactive power is being injected. The reactive power which was less, the reactive power injected by SSSC which was less earlier, it now increases. So this shows it is because of injection of the voltage. So that means when reactive power is injected into the line, that increases the power transfer capability of the line. I have already explained that overall impedance of the line decreases, or effective voltage across the line increases, and current increases, and power flow which was less without compensation, now more power is flowing. You can see. Now, इसके बाद क्या होता है? This is the compensation for negative power. Negative power में क्या होता है? Current reverses its direction. You can see, so for example, this is current. Now current will not go through the positive half cycle. It will have negative half cycle. And then positive half cycle. Let me follow this. Negative, positive, negative, positive, negative, positive. So IA has reversed. Okay, because for negative power flow, the current, the power is now flowing from receiving end to sending end, and you can see current is in phase opposition with the voltage. So current has reversed its direction. यहाँ पे भी मैं current reversal दिखा रहा हूँ, and this is the injected voltage. Now let me show you injected voltage. And you know, for reverse power flow, I have already told you that magnitude of injected voltage should increase. It should become greater than Vs minus Vr. If here injected voltage was less, here for reverse power flow it has to increase. So let me show you increased injected voltage. It is again out of phase with current by 90 degrees. It's in quadrature with the current. You can very clearly see this is the injected voltage VQ, and as compared to this, its amplitude is increased because of it has to fulfill this condition, that VQ is greater than difference of sending end and receiving end voltages, Vs minus Vr, and therefore it results in reversal of the current and hence reversal of power flow. That means now power is not flowing from sending end to receiving end, it is flowing from receiving end to sending end. You can see this is positive power and then it becomes negative active power. So therefore these waveforms clearly show the situation when there is no compensation, the situation when there is compensation for positive power flow, and compensation for negative power flow. For no compensation, SSSC does not inject any voltage, VQ is equal to 0. For positive power flow compensation, it injects certain amount of voltage VQ which is in quadrature with the current, and for negative power flow the magnitude of injected voltage increases so that this condition is fulfilled and direction of power flow reverses. I hope this is clear. Now just like other compensators, like whether it is GCSC, TSSC or TCSC, which I have already discussed with you, they can be used in voltage compensation mode or impedance compensation mode. Your SSSC can also be used in two modes, voltage compensation mode and current compensation, impedance compensation mode. First of all, we will discuss voltage compensation mode. How SSSC is used in voltage compensation mode. Voltage compensation mode. I have already told you that, for example, this is your SSSC. देखिए ये आपका SSSC है. This is the injected voltage VQ. This is the transmission line current I. This is your SSSC converter. This is DC bus, VDC, and this is SSSC converter. And you know, the reactive power exchange it is doing. और ये आपकी transmission line है. And transmission line has certain inductance, XL, and voltage across transmission line inductance is VL. Now in the voltage compensation mode, certain amount of voltage, we know that when SSSC injects the voltage, the injected voltage is independent of current. Whereas if this was a capacitive, series capacitive compensation, is in series capacitive compensation, the compensation voltage VC, that's the voltage across capacitor VC, that is minus JI into XC, that is dependent on current. As transmission line current varies, the compensation voltage VC also varies, but that is not the case with SSSC, because SSSC is basically an inverter, and inverter injects certain amount of voltage which is independent of this transmission line current. Whatever the transmission line current, it is independent. So therefore, if we design the SSSC compensator in such a way that it injects the maximum voltage and it does the maximum voltage compensation, and that injected voltage will remain independent of your current, transmission line current, and that I can show like this. This is transmission line current I. This is inductive voltage VL. This is capacitive voltage VC, because we already know that this SSSC can be made to operate in the inductive region or in the capacitive region. In the capacitive region, this is the direction of voltage, I mean polarity of voltage, instantaneous polarity voltage. And if you want to operate this SSSC in the inductive region, then the polarity of voltage can be reversed. It can be in this direction. Okay. Now, let us suppose we are operating our SSSC in the inductive region, and in the inductive region it is injecting voltage VQ, and this VQ is equal to VL max, maximum inductive voltage. So therefore it is doing maximum inductive compensation. And on the other hand, if you are using your SSSC in the capacitive region, it is injecting a voltage VQ which is equal to VC max, which does the maximum capacitive voltage compensation. And then this, whether it is VL max or VC max, it is independent of current, transmission line current. So for example, here transmission line current is maximum, it is I max. And here transmission line current is, say, for example, I min. Whether your transmission line current is minimum, less than minimum, or greater than minimum, or it is at maximum value, you can see the injected voltage VQ, which is equal to VL max for inductive mode of operation, or which is equal to VC max for capacitive mode of operation. It is independent of the current. It does not depend upon the current. So you can see it is independent of the current. So therefore, we can use SSSC in the voltage compensation mode, and if it injects certain amount of voltage for series voltage compensation, that voltage remains fixed, that is independent of the current. You can see as the current varies, the compensation voltage does not vary. It remains here VL max, here in the capacitive region it remains VC max, independent of the current. So I can just shade these inductive and capacitive regions. And what about the losses? Let me show you the losses, percentage losses of the converter or SSSC. This is 0%, 0.5%, 1.0%. This is maximum current. These are very small losses if injected voltage is 0. I mean, if your SSSC is not injecting any voltage, VQ is equal to 0. So that means it is not injecting any reactive power into the transmission line. However, there is always a transmission line current flowing in the secondary winding of the coupling transformer. You can see this is a coupling transformer primary winding, this is secondary winding. Always this transmission line current is flowing there, and therefore since converter is not operating, it's not injecting any voltage, means it is not operating, it is off. It's not injecting any voltage. So converter losses will be zero. However, there will be small losses in the transformer secondary winding. And as the current, transmission line current increases from 0 to I max, these losses will increase. However, these losses will be very, very small. VQ is equal to 0, as you can very clearly see. On the other hand, if this SSSC is used for compensation, voltage compensation, say in the capacitive region, when it is used in the capacitive region for, or in the inductive region for voltage compensation, it injects certain amount of voltage VQ, which is, say for example, equal to VC max, and then there will be losses. As the transmission line current increases, there will be more and more losses in the transformer primary winding as well as secondary winding, and there will be additional losses in the converter switches, because inverter is now operating. It's injecting the voltage in series with the transmission line via this coupling transformer. That means when inverter is operating, the switches are carrying current. I mean, there will be conduction losses and switching power losses in the converter switches, because we are using this converter in the PWM mode of operation, and in the PWM mode of operation we are using it at a higher frequency of the order of tens of kilohertz. So there will be switching power losses. So therefore losses will be appreciable, quite high. These are the losses for VQ max. Okay, these are very, very close to unity. I mean 1.0 per unit value. So as the current increases, the losses in the SSSC also increase because of switching power losses, and because as the current increases, the transformer losses are also increasing. Okay, for VQ equal to 0, there was loss in only transformer secondary winding. No current was carried by the primary winding because inverter was off, and there were no switch losses in the inverter. But now when inverter is operating, it is injecting voltage, there will be switching power losses and conduction losses in the converter switches plus transformer losses. So as the transmission line current increases, these losses will appreciably increase. Okay, what about the rating of SSSC? How do you find rating of SSSC? Rating of SSSC will be equal to maximum injected voltage VQ max multiplied by maximum transmission line current I max. So for example, here transmission line current is I max, and how much is the voltage, say in the capacitive region? It is VQ equal to VC max. So this, if you know how much voltage it has to inject, what's the maximum voltage the converter has to inject, and at what current it has to inject that voltage, you can find the rating, MVA rating of SSSC converter and MVA rating of transformer. Okay, so this is voltage compensation mode. Similarly, we can discuss or we can draw the characteristics for impedance compensation mode. Impedance compensation mode. Impedance compensation mode. In the impedance compensation mode, the characteristics will be like this. This is inductive voltage. Again, this is capacitive voltage. This is transmission line current 0, right? So this is, let me first of all draw, then I will explain. This is maximum transmission line current. This is the maximum injected voltage VQ equal to VC max, and here injected voltage by SSSC is VQ equal to VL max. Okay, so therefore this shows XL max, maximum inductive reactance, and this shows XC max, because this SSSC can behave as a reactance just like a capacitor. What is the reactance of SSSC? It is VQ by I, this I, transmission line current. Injected voltage by current will give the reactance of the SSSC. So therefore, when SSSC is carrying, when transmission line current is I max, and when at that time the maximum voltage which is injected by your SSSC is VL max in the inductive region, the reactance or the impedance offered in series with the transmission line by this SSSC is XL max in the inductive region, and in the capacitive region corresponding to maximum capacitive current, maximum transmission line current, and maximum capacitive voltage or maximum injected voltage, the capacitive reactance which is put in series with the transmission line is XC max. Okay, so in a similar way we can draw losses when we operate SSSC in impedance compensation mode. So again, these are percentage losses. So for example, this is 0.5, this is 1.0, this is I max, maximum current. Losses are very small for XQ equal to 0. If no compensation is done, the reactance which is put in series with the transmission line by SSSC is 0. However, as the transmission line current increases, some losses will be there because this current has to flow through the transformer secondary winding. So there will be I square R losses and maybe some core losses, etc. in the transformer and the losses, although low, but these losses will be there. But when you are operating your SSSC for compensation, say impedance compensation, and you are injecting the maximum voltage VQ equal to say VL max, or VQ equal to VC max, maximum voltage, then maximum impedance will be there put in series with the transmission line, and there will be losses, higher losses, because now since inverter is operating in the PWM mode of operation, there will be higher conduction and switching losses plus transformer losses, and these losses will be very, very high. So this is for XQ max. If you are operating your SSSC as a maximum impedance, maximum reactance, so losses will be high. So this clearly shows operation of SSSC and losses in the impedance compensation mode. And finally, let me tell you, since this SSSC is basically a converter, a voltage source inverter, the size of inverter may be very large, the rating of inverter may be very large, and cost of this series compensator may be higher than the cost of other series compensators like GCSC, TSSC, and TCSC. In order to reduce the overall cost of this compensation scheme, what some researchers have done, they have proposed hybrid compensation scheme. Well, let me discuss briefly with you what is hybrid compensation scheme. Hybrid compensation scheme. In hybrid compensation scheme, what they do is that instead of using SSSC alone, compensation is done in a hybrid mode by fixed capacitor. Say for example, this is the capacitor with capacitive reactance XC, and this is the capacitive voltage VC. Right here, capacitor is XC, voltage VC, and then we have SSSC. This is voltage injected by SSSC through the coupling transformer, which is shown here, and this is our SSSC converter, which is a voltage source converter or voltage source inverter. This is its DC bus, right? And it exchanges, say, reactive power with the system. And this is the normal transmission line reactance XL with voltage VL. Transmission line current is I. So instead of doing compensation by SSSC alone, this is SSSC converter, SSSC, we are doing partly compensation by SSSC. Say 50% of compensation is done by SSSC and 50% compensation is done by capacitor, fixed capacitor, which is put in series with the transmission line. So the rating of this capacitor bank is 0.5 per unit, and the rating of this SSSC is also 0.5 per unit. So we are able to reduce the rating and hence size of SSSC converter and SSSC transformer, so that reduces the cost. And hybrid compensation is done. It is done both by series capacitor as well as SSSC. Okay, so it is hybrid mode of compensation, and total compensation voltage, let's call that V compensation, that is equal to compensation voltage of capacitor plus compensation voltage of SSSC. And if I write compensation voltage of SSSC is VQ, what is a compensation voltage of capacitor? It is minus JI into XC. So then minus JI into XC. Okay, so this is hybrid compensation. The advantage of this hybrid compensation is that the rating and the cost of SSSC converter is decreased. Its rating is reduced by 50% and hence cost is also drastically reduced. Losses also get reduced, okay, because SSSC, say previously if compensation is done by SSSC alone, its rating may be 10 MVA. Now if we do the hybrid compensation by partly 50% compensation by fixed capacitor and 50% by this SSSC, the rating of SSSC is only 50%. So its rating is decreased from 10 MVA to 5 MVA. So its rating decreases, size decreases and cost decreases. So cost of SSSC with this hybrid compensation decreases. And not only cost, the losses also decrease because the current carried by the SSSC switches because of decrease in the rating from 10 MVA to 5 MVA, the losses obviously will reduce. Okay, so this is the advantage. Okay, however, the drawback is that in this case the series compensation is not completely independent of the current, because compensation is done by SSSC and the compensation voltage of SSSC VQ is independent of current, but the compensation voltage created by capacitor VC is not independent of current. You can see it is dependent on current. It is Ji into Xc. As transmission line current varies, this compensation voltage also varies, and therefore it will have effects on VI characteristics. So let us draw VI characteristics again. VI, voltage versus current characteristics, or let us try to understand operation of this hybrid compensator in voltage compensation mode. Voltage compensation mode. So in voltage compensation mode, the operation is like this. This is transmission line current I. So this is VC, this is VL. Let us suppose the voltage injected by when transmission line current is 0, the SSSC is operating and it is injecting a voltage VQ in the system, and that VQ is equal to VL max, maximum voltage compensation it is doing. But then as the transmission line is loaded and current increases, the compensation voltage of capacitor also comes into picture. Here when transmission line current was 0, and since the capacitor voltage is minus Ji into Xc, when current is 0, Vc is 0. So only this VQ compensation will be there, and this VQ will be equal to VL max. We designed the compensator in such a way that this compensation voltage is maximum compensation voltage VL max. And you have seen previously, just few moments back, when compensation is done only by this SSSC, this remains constant, independent of the current, but now it will not remain independent of current, because part of the compensation is done by this fixed capacitor, and this capacitor compensation voltage is dependent on current. So as the transmission line is loaded and transmission line current increases, this VC increases. So therefore, what is your total compensation voltage? As per this equation, it is VQ minus Ji into Xc. So ये Ji into Xc इसमें से subtract हो जाएगा, so it will go on reducing till I is equal to, say for example, I max. When transmission line current is maximum value, this voltage and this voltage, they are equivalent. I mean, this voltage VC subtracts from VQ and total compensation voltage becomes equal to 0, and this is the problem. However, the design is done in such a way that for a given amount of transmission line current, the compensation voltages created by SSSC and this fixed capacitor, they are adjusted in such a way that certain amount this VQ is not 0. I mean, compensation voltage is not 0. It is not maximum also. You can adjust it somewhere between maximum value and 0 value. Okay. This is if you are operating it. So this is VC plus VQ. And in the capacitive region of operation, VQ is equal to VC max. Again, when you are using this compensate in the inductive mode of operation, this voltage was in this direction and capacitive voltage was in this direction. So that's why they were subtracting each other. And as current was increasing, this voltage was increasing, ये इसको subtract कर रही थी, और finally at certain amount of current, say transmission line current I max, total compensation voltage was become equal to 0. But in the capacitive region of operation, when you are using the SSSC in the capacitive region of operation, the direction of voltage reverses. It is like this. So these two voltages will now add. So when transmission line current is 0, this VC is 0 and VQ is equal to VC max. And as the transmission line current increases, this VC also increases. And since this voltage adds to this voltage, the total compensation voltage becomes greater than VC max. ये increase होती है. So this is VC minus VQ. That is VC क्या है आपका, VQ क्या है आपका, VQ is VQ minus VC, और VC है आपका minus J into minus into minus plus हो जाता है J I into XC. So the two voltages add. Here also you can see the two voltages add. Total compensation voltage at maximum transmission line current is higher than the maximum voltage. So therefore now this hybrid compensation has one drawback, that the compensation voltage, unlike SSSC alone, where the compensation voltage was remaining fixed, independent of current, it is now varying with the current, both in the inductive region as well as in the capacitive region. And what about losses? Let me show the losses. Losses will reduce. This is transmission line current versus percentage losses. This is 0.5 per unit losses, 1 per unit losses. Say for example, this is I max, maximum transmission line current. This is if compensation voltage is 0, if no compensation voltage is injected by SSSC, losses are less. But then when SSSC is injecting the compensation voltage, there will be losses in the inverter, SSSC inverter, and small losses in the capacitor. Capacitor losses will be negligibly small. Mainly there will be losses in the converter and some losses in the transformer. But since the rating of converter has reduced from 1 per unit to 0.5 per unit, the losses will also reduce by 50%. So this is for VQ max. And if you compare this graph with the previous graph when SSSC was used alone, there at VQ max, maximum compensation voltage, at maximum transmission line current, the loss was very close to 1. Here it is just 0.5. It has reduced by 50%. Okay, fine. This is in voltage compensation mode. And what about current, this impedance compensation mode? Let me very quickly show operation of this hybrid compensator in impedance compensation mode. Impedance compensation mode. Let me first of all draw the characteristics. These are basically VI characteristics. So this is inductive voltage, capacitive voltage. Okay, let me first of all draw and then I will explain. This is transmission line current I max. Okay, here it is XC plus XQ, total reactance. And here this is VQ equal to VL max. Let me first of all draw, then I will explain. And this is VQ equal to VC max. So here total reactance is XC. I have already written XC plus XQ, and here it is XC minus XQ. Now when current is injected, voltage is 0. Okay, when current is 0, impedance is 0, and then as the current increases, for Imax, I have designed my SSSC compensator in such a way that it gives maximum compensation, maximum reactance, XQ. Okay, but what happens as the current increases? This XC in the inductive region, in the inductive region, what will happen? XL is the reactance, XC is the reactance of this capacitor, और इसकी reactance क्या है? Say XQ. Okay, in the inductive region, the voltage is in this direction, and as the current increases, the reactance increases. उसके बाद क्या होता है? Up to till VQ is equal to VL max, till maximum voltage. Here VQ is equal to VL max. उसके बाद जो ही current फिर से increase होती है, it increases. The total reactance decreases. Okay, the total reactance will decrease, because the reactance of this SSSC will subtract from reactance of this fixed capacitor. However, in the capacitive region of operation, as the current increases, the reactance will increase. Why it will increase? Because our SSSC is operating in the capacitive region of operation, and total reactance will increase. And when I is equal to I max, the VQ is equal to VC max. This is the total reactance. Okay, capacitive. This is the total reactance which is put in series with the transmission line by both fixed capacitor as well as SSSC. Okay, what about percentage losses? Let me just show percentage losses below or beneath it. Percentage losses, this is 0.5 per unit, 1 per unit. Losses are very small if XQ is equal to 0. That means when SSSC is off and when SSSC is on, and it is designed to inject maximum voltage, so that XQ is equal to XQ max. This is XQ max. Losses are reduced. You compare these losses with the previous case when SSSC alone was operating. There the at I max, maximum transmission line current, loss was nearly equal to 1 per unit. Here it is reduced by 50%. It's only reduced nearly by 50%. It's only 0.5 per unit, because SSSC की rating कम हो गई है 0.5. It is rating is decreased by 50%, so losses also get reduced. Okay, so therefore this scheme, hybrid compensation scheme, which comprises of fixed capacitor, series capacitor compensation plus SSSC series compensation, it results in reduced power losses, although compensation voltage to some degree becomes a function of line current. So therefore, advantage of this hybrid compensation scheme is that it reduces the overall cost, the overall rating of SSSC, the cost of SSSC reduced, and losses also reduced. But the drawback is that the compensation voltage to some degree becomes a function of line current, which I have clearly shown with the help of various graphs. That's all about SSSC. So now it is your choice. If you have money, you can propose a project and you can design an SSSC for series compensation, because SSSC is very versatile series compensator. It is better than all other compensators, but its cost is high, rating is high, and if there is a constraint, I mean cost is the factor, then you can go for hybrid compensation, because in hybrid compensation using fixed capacitor, fixed series capacitor and SSSC converter, the rating of SSSC converter decreases by 50%. The rating of coupling transformer also decreases by 50%. Cost is reduced by 50%. Losses are also reduced. Okay, but the problem is that compensation voltage or compensation to some degree becomes a function of line current. So that marks the end of our discussions on series compensation by SSSC. Okay, so and that of course marks the end of our discussions on various methods of series compensation. If you remember, over the last few lectures we have been discussing series compensation, first by GCSE, that is GTO controlled series capacitor, then by thyristor switch series capacitor, this is also a series compensator, then thyristor controlled series compensator, and finally static synchronous series compensator. These are 4 types of series compensators that we have discussed over last 3 to 4 lectures or 4 to 5 lectures. These 3 are thyristor based series compensators, thyristor based, and this SSSC is converter based series compensator. As far as GCSE is concerned, it gives variable capacitive reactance, and capacitive reactance changes from 0 to XC max by delay angle control, by turn off delay angle control. If you remember, just go through that lecture, just revise that. Turn off delay angle control, which is also called gamma control. By gamma control, if you change gamma from 0 degree, if gamma is changed from 0 degrees to 90 degrees, you are able to change your capacitive reactance, which is put in series with the transmission line by GCSE, from 0 to XC max. For gamma equal to 0, capacitive reactance is max, XC max. And as gamma is increasing from 0 to 90 degrees, it decreases. And at gamma equal to 90 degrees, capacitor reactance is 0 because your GCSE turns off. GCSE, I mean, it does not turn off, it remains on only. Okay, so at gamma equal to 90 degrees, capacitor reactance is Xc. It's not, in fact, it is not. Yeah, at it is 0, and at gamma equal to 0 degree, it is maximum. Xc max. Okay, what about TSSC? And it gives continuous control. Since gamma control is continuous control is achieved. On the other hand, thyristor switch series capacitor, TSSC, it also gives us capacitor reactance which is variable from, say, 0 to Xc max, but not continuous control. Not continuous control. It gives stepped control. Not continuous control, but control in steps. You have one TSSC, you can either turn it on or off. So if it is on, depending upon its condition, it gives a certain amount of capacitor reactance. Then if you have another SSSC in series, you turn that on or off. By controlling that, the reactance increases, say, Xc plus Xc, 2Xc, then 3Xc or so. So therefore the capacitor reactance is not continuously varied, say like in GCSE from 0 to Xc max. It is varied in steps. It gives stepped control. And regarding TCSC, I have already told you, TCSC has a unique feature. It can operate in the inductive region as well as capacitive region. If it operates in the capacitive region, it gives the its reactance varies from minimum value Xc, XTCSC, which is a function of alpha, to Xc max. That means if your delay angle range is alpha C lim less than or equal to alpha less than or equal to 90 degrees, at alpha equal to alpha C lim, the capacitive reactance is maximum, Xc max. And as, let us start from 90 degrees. When alpha is equal to 90 degrees, your capacitive reactance, that means your TCR is not on at all. Capacitive reactance is minimum, and that is equal to normal capacitive reactance of the capacitor, which is equal to 1 by omega C. It's not possible to get capacitive reactance down to 0 as in other cases. Here you can get capacitive reactance minimum values, normal value 1 by omega C. And then as delay angle is reduced from Xc max, from 90 degrees to alpha C lim, the capacitive reactance goes on increasing till you reach alpha C lim, at which capacitive reactance is maximum, Xc max. And you can operate the same TCSC in the inductive mode of operation. And in the inductive mode of operation, XL less than or equal to X TCSC, which is a function of alpha, less than or equal to XL max. And the range of delay angle is 0 to alpha L lim. When alpha is equal to 0, the reactance of TCSC, inductive reactance, is XL equal to, it is XL minus XC divided by XL minus XC, where XL is equal to omega L. And as delay angle is increased from 0 to alpha L lim, the reactance increases till at the alpha L lim you reach maximum inductive reactance. So therefore TCSC can be operated in inductive mode of region, in inductive region as well as in capacitive region, and it gives variable inductance, inductive reactance in the, if it is operated in the inductive region, and variable capacitive reactance if it is operated in the capacitive region. Okay, and finally, over the last couple of lectures, we have discussed converter-based series compensator SSSC. The unique feature, the SSSC also, just like TCSC, is capable of operating in the inductive mode as well as in the capacitive mode. In the inductive mode, it gives variable reactance, capacitive reactance, 0 to Xc max, and in the of course, depending upon the injected voltage VQ, which is a function of sigma, it varies from VQ to VQ max. When injected voltage is 0, capacitive reactance is 0. When injected voltage is increased from 0 to VQ max, capacitive reactance increases from 0 to Xc max. Okay. And in the inductive region, it gives variable inductance, inductive reactance 0 less than or equal to XL less than or equal to XL max. And injected voltage is 0 VQ sigma less than or equal to minus VQ max. If you want to operate your SSSC in the inductive region, then the injected voltage, its phase should reverse. Okay, it should be opposite polarity. For example, for capacitive mode of operation, if this is the polarity of injected voltage by SSSC, for operating in the inductive region, its polarity of injected voltage should reverse. So its polarity should reverse. And by controlling this reversed injected voltage from 0 to minus VQ max, you can make inductive reactance of SSSC to vary from 0 to XL max. And then another feature of this SSSC is that you can make power flow reversal also, which is not possible with any other series compensator, thyristor based series compensator. That's done only by SSSC. Direction of power flow can be changed if injected voltage VQ is made greater than Vs minus Vr. I have shown that few moments back with the help of waveforms. So if normally power flows from sending end to receiving end, and after fulfilling this condition, we can make power to flow from receiving end to sending end. So power flow reversal is also possible with SSSC. And then in order to reduce the cost, size, cost, and losses of the series compensator using SSSC, we can go for hybrid compensation scheme, which comprises of fixed series capacitor and SSSC put together. Okay, this hybrid compensation scheme is cheap. It gives reduced losses, but the problem is that compensation voltage to some degree it becomes a function of line current. That's all. So this was an overview of or a summary of various types of series compensators. 3 thyristor-based series compensators, GCSC, TSSC, TCSC, and 1 converter-based series compensator, SSSC, which we have discussed over last 4 to 5 lectures. And this marks end of discussions on series compensators. And I am happy to announce that this marks end of module number 3. So module number 3 of your syllabus is over. Now we are left with only one module, module number 4. Inshallah, from next lecture we will start module number 4. And in module number 4 we have to discuss series compensators, combined series compensator, combined series shunt compensator, then thyristor controlled voltage regulator, thyristor controlled phase angle regulator, and thyristor controlled braking resistor. Some 4 to 5 types of FACTS controllers we have to discuss. We have already discussed shunt compensators, and today we have completed our discussions on various types of series compensators. Now that marks the end of module 3. From next lecture onwards, we will start our module 4. So I advise all of you to revise whatever we have discussed over last few lectures, especially these series compensators, and make a comparison between various types of series compensators. In case of any doubts, please feel free to ask. All the best to all of you. Thank you.